Hi everyone, my name's Ethan Sacoransky and I'm a first-year radiology resident at the University of Saskatchewan. And I'd like to thank my co-authors Yash Chauhan, second-year medical student, and Dr. Scott Adams, cardiothoracic radiologist, for co-authoring and contributing to this project. The title of our project is Artificial Intelligence for CT and MRI Protocoling, a meta-analysis of traditional machine learning, BERT, and large language models. And the authors have no conflicts of interest to declare. And the motivation for this study goes back to a radiology elective that I did as a medical student. I remember working with the radiology resident, and twice a day, usually in the morning and after lunch, a nurse would bring in a stack of clinical imaging requisitions that needed to be protocoled by the resident. And I thought that this was interesting and that, it got me thinking maybe there could be a more efficient way to protocol these requisitions that doesn't take up so much time out of the radiologist's daily workflow. And one of the solutions to this problem is the utilization of AI for automated radiology protocoling. In the literature, this has really fallen into three categories. One is traditional machine learning. Two are BERT models, which is essentially a newer type of machine learning model that came out around 2018. And then number three is LLMs, that includes, for example, ChatGPT, Google Gemini, Llama, or DeepSeek. And these are the latest state-of-the-art AI technology. And so the objective of this particular study was to do a systematic review and meta-analysis on CT and MRI automated protocoling using AI. We knew that there had been individual studies published on automated protocoling with AI, but to our knowledge, there had not been a meta-analysis done to synthesize all the studies for this application so that we can get a better idea of how accurate they actually are. In terms of the search strategy, we looked at several databases and went all the way from inception through to July of 2025. And the search strategy was specifically designed to look at the intersection between AI, CT/MRI, and examination protocoling. For our inclusion criteria, it needed to be a primary peer-reviewed study published in English that used AI to assign exam protocols. The imaging modality needed to be CT, MRI, or both. And the study needed to report at least one quantitative metric of AI performance. So, for example, the accuracy of protocoling. And then lastly, the study needed to have a clear reference standard, whether that was a radiologist consensus or the clinically assigned protocol. An exclusion criteria included protocoling modalities, for example, ultrasound or X-ray that did not include CT and MRI, a study that did not utilize AI for this task, and a study that focused on, say, image reconstruction, segmentation, etc., as opposed to focusing on protocol assignment. In terms of our Prisma diagram, we started off with over 3,500 abstracts from various databases, and we were able to distill that down to 23 final studies that included 16 traditional machine learning studies, 8 BERT studies, and 5 LLM studies. For the included studies, there was over 1 million imaging requisitions that was included overall. All these studies were retrospective, published between 2017 and 2025, and this included 10 US studies, 6 from Canada, 3 from Germany, 1 from each of Finland, Japan, Spain, and South Korea. If we look at all the 23 studies that comprised 57 different artificial intelligence models, the overall protocoling accuracy was 85% across all studies. When we look at the subset of studies that looked at traditional machine learning models, we get 16 studies, 3 of which used fine-tuning. And as expected, the traditional machine learning studies had the lowest pooled accuracy of 83%. When we compare it to the BERT models, which had a higher accuracy, and the LLM models, which also had a higher accuracy. And the BERT models had the highest pooled accuracy of the three model classes, with a pooled accuracy of 87%. And all 8 studies that looked at BERT models utilized fine-tuning. What was really interesting about the BERT studies is that some of them would just output a single protocol, but in some of the studies, what they designed the model to do is return the top 2 or 3 candidate protocols in more difficult scenarios to allow a radiologist to make the final decision. And then in some studies, the model would assign a probability to each requisition that it needed assistance from a radiologist. And if it was a high probability, then it would send it off for a review and protocoling from the radiologist. Whereas if it had a low probability, then it would do it itself, bypassing the radiologist. And that's an application that could potentially be used in the future as we look at hybrid AI radiologist workflows within the radiology clinical environment. In terms of LLMs, there were 5 studies that used LLMs for the protocoling task, and only 1 of 5 studies used fine-tuning. In terms of the pooled accuracy, it was 86%, which was slightly lower than the BERT models, but higher than the traditional machine learning models. If we look at a violin plot of the 3 subgroups, the traditional ML models had the lowest accuracy and the highest spread, where each black dot represents an AI model. Then the BERT and the LLM models had a lower spread, similar accuracy, although BERT was slightly more accurate than the LLMs. And overall, when we compare the 3 different classes, there was no significant differences in accuracy between any of the 3 subgroups. The individual AI models were able to be plotted in a heat map, and if we look at the 10 most accurate models, 6 out of the 10 were from BERT-based models, 2 out of the 10 were LLMs, and 2 out of the 10 were traditional machine learning models. To look further at the studies as subgroups, we did subgroup analysis on imaging modality, requisition language, and subspecialty. In terms of modality, 6 studies looked only at CT, 10 looked at MRI, and 7 looked at both CT and MRI. In terms of language of imaging requisition, 20 of the 23 studies used English, but 1 study used Finnish, 1 used Spanish, and 1 used Japanese in terms of the imaging requisitions that were fed into the AI model. And then lastly, the subspecialty subgroup analysis, where we had body imaging, MSK, neuroradiology, thoracic imaging, and multiple subspecialties that were analyzed. When we look at subgroup analysis by imaging modality, the pooled accuracy of the CT studies was 83%. The pooled accuracy of the MRI studies was 85%, and the mixed studies was also 83%. When we look for significant differences between the subgroups, the difference was not statistically significant. When looking at requisition language, the English requisitions studies had a pooled accuracy of 85%, whereas the studies utilizing non-English language requisitions had a pooled accuracy of 81%, which was a statistically significant difference, demonstrating that AI models with inputs in English performed better than studies using inputs in non-English based languages. Looking at imaging subspecialties, the accuracy ranged from 84% up to 88%, depending on which subspecialty you were looking at. And when we compare any 2 subspecialties, there was no statistically significant difference between the groups. And a very important part of this study was to look at sources of error. So why were these AI models making mistakes in protocoling? One main source of error was ambiguous or underspecified requisitions that were vague in terms of their language. And this is a scenario where even radiologists had variation in opinion as well. Another example is very non-specific symptom descriptions within the requisition. And then another one is when the anatomic detail was not specified or very general. That led to higher degree of incorrect protocols. Another common source of error were studies that had requisitions that combine multiple clinical questions into one requisition. Those were often missed by the protocoling model. Another common source of error was related to class imbalance, where the models performed best on common protocols that were also commonly found in their training data, whereas rare protocols, they performed much worse, partly because those rare protocols by definition are rare and they don't show up very often in their training data sets, so they didn't perform as well in those areas. And the last area of error analysis that came up were protocols that had multiple correct answers. For example, to rule out a ureteric stone, an unenhanced KUB-CT, and a CT abdo-pelvis unenhanced were both reasonable answers, but we needed to have one correct answer per protocol, so that came up fairly often. And in the various studies that looked at that, there was even a fair amount of variation among radiologists themselves, reflecting the fact that in many scenarios there can be more than one correct protocol. So in conclusion, this is a meta-analysis of 23 studies evaluating the performance of AI-based automatic protocoling of CT and MRI requisitions. The pooled accuracy was 83% for traditional ML, 87% for BERT, and 86% for LLMs. There was no significant difference between the three approaches. However, 6 of the top 10 performing models were within the BERT category. So this begs the question, if LLMs are regarded as the state-of-the-art AI technique, why did the BERT models perform better in our analysis? And we opined that the likely reason for this is because all the BERT models in the analysis underwent fine-tuning, whereas only one of the 5 LLMs reported fine-tuning. And it's pretty well established in the literature that fine-tuning an AI model leads to better performance in radiology-related clinical tasks. And moving forward, until fine-tuned LLMs are specifically tested with enough of a sample size, their performance relative to BERT models still remains uncertain. For future work, we think that this can focus on fine-tune LLMs for this task, as well as the utilization of hybrid workflows that combine AI and radiologist input. We do think future research should prioritize the errors that we identified, prioritize ways to combat these errors or minimize these errors within an AI workflow. And then obviously patient privacy and EMR integration will be a focus. In terms of study limitations, there was significant statistical heterogeneity. There was a predominance of English requisition corpora, and there was also inherent protocol variability even among radiologists, which challenges the notion of a single correct reference protocol. In summary, this is a first meta-analysis evaluating the performance of machine learning for CT and MRI protocoling. And these tools overall show very strong potential to help streamline radiologist workflows, possibly through hybrid AI radiology approaches. And then in the future, we need ongoing exploration of fine-tune LLMs and development of novel solutions to identify these model errors. Thank you very much for listening. I hope you enjoyed, and if you have any questions, please let us know.